everyone, I am Jin Lujia from Peking University. This is a joint work with my colleagues Zhao Shi, Zhu Lei, Chen Qian, and Lu Yanye. Here I will introduce our paper One-Port Multi-Frame Denoising. According to the situation of the image in the dataset, we classify deep learning-based image denoising methods into 4 categories from the perspective of supervision strategy. A paired noisy and clean image is the most naive case, corresponding to supervised N to C. Although the vast majority of denoising methods belong to N to C, it is difficult to obtain clean labels in most real-world scenarios. However, in almost all scenarios, a single noisy image is available. Methods that only use a single noise image for denoising, such as N2S, N2V, and DIP, all belong to self-supervised methods. They completely relax the strict requirements of the data, but the performance of denoising is often not satisfactory. In addition to these 2 categories, in many real-world scenarios, multiple noisy images corresponding to the same region of interest are available. If at the same time we can get the corresponding clean images as labels, we can use supervised methods such as KPN, MKPN, and BPN for denoising. However, in most cases, clean labels are not available, so unsupervised N2N can be used for denoising. The disadvantage of N2N is that utilization of multiform data is insufficient when N is greater than 2. As just said, in real-life scenes, the acquisition of multi-frame images is available and even natural, such as in burst photography, explorer bracketing, astrophotography, and OCT. However, denoising methods for multi-frame images are rarely studied, especially unsupervised methods. This is a gap in denoising research. Supervised methods suffer from the lack of clean labels. Self-supervised methods perform relatively poorly. As for unsupervised double from N to N, although it has a good balance between denoising performance, penalty, and labeling requirements, it doesn't fully utilize multi-frame data. So, OPD is proposed in this paper. As an unsupervised method, OPD doesn't require clean labels and is able to boost denoising performance by fully exploiting the inter-frame mutuality of multi-frame data. Overall, the contributions of our paper are mainly in 3 points. First, we propose the first unsupervised multi-frame denoising method, OPD. Second, we propose 2 specific implementations of OPD, OPD-RC and OPD-AL. Third, experiments show that OPD behaves as the SOTA unsupervised method and is comparable to supervised N to C for several multi-frame denoising tasks. This is an overview of the principles of OPD. It is based on neutral supervision among multiple frames. The roles of the 2 noisy images participating in the training under mutual supervision are not absolutely prescribed, but interchanged, entangled, and equivalent. Furthermore, for multi-frame scenarios with more than 2 frames, mutual supervision can be established among all frames corresponding to the same clean target. Diversified samples and labels enable the model to squeeze out much more hidden inter-frame information contained in the data during learning. At the same time, this also makes the model face more optimization possibilities. This potentially leads to an improvement in denoising performance. The most intuitive way to perform OPD is to go through all the one-to-one unidirectional supervision paths. But it is easy to realize that skyrocketing data size makes this weight so crude, considering that the learnable models usually look for the minimum in an iterative manner on the hypersurface defined by the loss function. From the perspectives of reconstruction of the iterative data paths and reconstruction of the loss function, we propose 2 feasible OPD implementation methods, OPD-RC and OPD-AL respectively. First, we introduce OPD-RC, where RC refers to random coupling. Given a multi-frame image set like equation 1, we can randomly and uniformly divide the M noisy frames into two sets like equation 2 and 3. Consider these two sub-data sets as inputs and labels respectively. According to the backpropagation rule, the model at step s plus 1 can be updated at theta subscript s plus 1 like equation 4. Next, repeat steps 2 to 4 until the model is fully converged. OPDRC makes each of the M noisy frames appear in each iteration with equal probability and serve as input or label with the same chance. This operation greatly extends the diversity of data pairing and supervision without any more training time consumption. This figure shows the general principle of OPDRC and its comparison with N2C and N2N. The data pairing way in the data allocator is the key difference between OPDRC and other supervision strategies. As shown in the lower part of the figure, we can see the key is that OPDRC randomly shuffles and repels the data after each iteration of model training. Next, we explain the principles of OPDAL. Under the most commonly used L2 norm, the objective of N2C learning is shown as equation 5. Replace f theta xi plus nij by yij and decompose LOPDC according to the polynomial theorem. We can get equation 6. At this time, Li consists of two items, Li1 and Li2. Further decomposition of Li2 is shown in equation 7. Substitute equation 7 into equation 6 to get the reorganized Li, which is shown in equation 8. Then substitute the reorganized Li into equation 5 to obtain the reorganized LOPDC, which is shown in equation 9. This is the pattern of OPD loss with clean supervision. Since Wu has proved the equivalence of convergence with clean or noisy labels, replace xi hat with its corresponding noisy frames. We can finally get the unsupervised OPD loss like what is shown in equation 10. The key constraint on interframe mutual supervision is the LMSA term, which reverses the interframe alienation mined by the model. When m equals to 2, equation 10 is reduced to the loss of n to n superimposed with mutual supervision. This shows that the proposed OPD is a generalized form of n-to-n. OPD is experimented in three typical scenarios: synthetic Gaussian and Poisson noise, and OCT speckle noise. Numerous representative methods are involved in the comparison. Here are two example results of denoising synthetic noise. Both OPDRC and OPDAL preserve high-frequency details better for both Gaussian and Poisson noise, such as the fringes on the hood skirt in the upper example and the texture of the sweater in the lower. Here is an example of denoising results on OCT. Obviously, the images denoised by OPD have sharper and more intact retinal layers, and the complex signal of choroid is not over-smoothed as in other methods. Let's compare the results of OPDRC and OPDAL. OPDAL processed images seem to be sharper than those OPDRC processed, both on synthetic noise and OCT. This reflects that the alienation loss may be slightly better than simple randomization. In addition to qualitative evaluation of image visual effects, quantitative evaluation was also performed, as can be seen from the table. For Gaussian noise, compared with N-to-N, the PSNR of OPDAL is improved by 0.88 dB, and ASIM is improved by 0.02, and the RMSE is decreased by 0.009. Similar boosts also occur on OPDRC and for Poisson noise. There is no doubt that OPD achieves SOTA among all unsupervised methods. Of course, it is reasonable that OPD as an unsupervised method is inferior to supervised multi-frame methods like BPM. However, OPD is still better than several supervised methods such as N2C and KPM. As an unsupervised method, this result is already satisfactory. For OCT denoising, among all the methods involved in the comparison, including supervised methods, OPDRC captures the SOTA result, and OPDAL is only marginally behind. The two OPD methods are the only methods with PSNR exceeding 30 dB. In addition, the SSIM of OPDRC reaches 0.9 and the RMSD reaches below 0.03. We explore the principles of OPD in more depth. An obvious question is that does the mutuality of supervision really help? We hold the view that the outstanding performance of proposed OPD stems from mutual supervision. In order to verify this point of view more practically, we reduce the number of frames to 2. At this time, mutual supervision means the random exchange of the sample and the label within data pairs during training. This is denoted as n2n sub s.5. From the quantitative results given in the table, it can be seen that n2n sub s.5 outperforms n2n in all aspects. Additionally, we simply learn data pairs in two supervision directions one after another, which is denoted as BDL, bidirectional learning. This twice-segmented dataset performs almost as well as n2n sub s.5. However, the rough augmentation of datasets consumes almost twice of training time that under n2n sub s.5. Furthermore, we conduct gradient experiments on the OCT dataset with probabilities ranging from 0 to 1. The results also show that the mutuality really boosts the performance of OPD on multi-frame denoising. Another question is that does the higher image multiplicity really help? Gradient experiments were carried out on OCT and the results are shown in the figure. From the figure, we can conclude that the greater the number of frames, the greater the number of mutual supervision combinations. Also, the greater the denoising performance. Okay, the above is the main content of our research. Thank you for your interest.